So I start talk. We study non-Bayesian belief updates, which is present in the question order QA, studied in cognitive psychology for a long time. Previous talk mentioned this effect in cognitive psychology. Wang and Gusmaya introduced the quantum model to explain the QA using project measurement models known as conventional models for quantum measurement. The project measurement or a projection postulate is a conventional rule for state change for quantum measurement. However, their models were criticized by the fact that their model violates another common effect called the response replicability effect, RRE. This was once considered as a false alarm for the quantum-like model approach to cognitive science advocated by Andre Krenn. Now we, Andre Krenn and myself, have shown that more general but physically realizable quantum measurement models can realize both effects consistently. Both effects means the QE and RRE. Such a class of general models for quantum measurements are called quantum instruments or quantum instrument models. Instrument theory was originally introduced by two mathematical physicists, E.B. Davis and J.T. Lewis. In 1979, I actually met E.B. Davis and actually at this institute. He was a member of the Mathematical Institute at Oxford University. And we discussed his motivation for this notion. The mathematical notion of the instrument is very complicated because they treat the mapping of the state, and the state is represented by mapping on the quantum state. The quantum state is represented by wave function. So the quantum instrument is very much higher hierarchy of the mappings of the quantum object. And in 1984, I solved the problem as to what instruments are physically relevant by introducing completely positive instrument, now known as quantum instrument. So we just apply this notion of the quantum instruments to this cognitive problem. Quantum measurement theory deals with state updates of the measured system. Our model describes the belief update as the state update of the mind state. So quantum theory treats the change of the quantum state. We apply the quantum mechanical mathematical apparatus to describe the belief update, means that the state update of the mind state. We further studied on the logical structure of the two questions manifesting in the quantum measurement model. We obtained the following. Belief update is Bayesian if and only it is projective and logically classical. So we consider the Bayesian update or non-Bayesian update. And we consider the projective update or non-projective update. And we consider the logically classical update or logically non-classical update. So belief update is Bayesian. If and only it is projective, means that they described by projective measurement. And the logically classical means that the projective measurement of the two observable which are commuting. So the logic for commuting observer is classical logic. The projective belief update satisfies QoE if and only if it is logically non-classical or non-Boolean. And the projected belief update satisfies RRE if and only if it is logically classical. So there is a contradiction between those two properties. So we cannot have the projected model which satisfies both quantum order effect and response replicability effect. From the above, the opinion poll data with quantum order effect and response replicability effect. We usually consider that the real statistical data from the opinion polls satisfy QOE and ROE. So that such a real data rejects the projected belief update conjecture. Thus, quantum instrument models are necessary. Quantum instrument model is more general measurement model broader than projective measure. In our model, the belief update is non-Bayesian and logically classical. Thus the statistics of opinion polls manifesting both QOE and ROE suggest that the brain logic for two questions is Boolean, but the belief update is non-Bayesian. So those poll data shows non-classical logic, classical logic, but non-Bayesian update. So the classicality of the logic is a consequence of functioning of our short-term memory. We consider that. So that there is a possibility of the situation in which consciousness manifests non-classical logic with non-Bayesian belief. Experimental studies for quantum instrument model will be called for. We don't have such kind of statistical data. This talk is based on the following papers by myself and Andrei Korenko, done from the 1919 to just not the present. So we start with reviewing the standard classical joint probability. The probability of obtaining the outcomes, random variable A1 takes a value A1, and that random variable AN takes a value of small n. Of sequential measurements of random variables A1 dot n. In this order, on the probability space omega to p is given by this formula, right? And this standard joint probability or successive probability for joint measurement of random variables, classical random variables, satisfy the following property. Repeatability it means that if you measure the same observable immediately, then you got the same result. The non-question order effect, the joint probability does not depend on the order of the measurement. And the response replicability effect is that does not happen that the first answer and the third answer are different when the same question is asked, or when you measure the same random variable in the first and in the third case. So they always reproduce the same answer. How many minutes?
We've been going for 10, so you still have including questions.
Very quick question. There's no time in that picture, right? It's all simultaneous measurement.
Yes, but this particular case we consider the successive measure. Immediately afterward. Yeah, it's the first subject.
Yeah.
conditional probability is just the notion of the Bayesian update. The standard classical joint probability is explained Bayesian update rule as follows. The joint probability distribution B given the preceding without A is small a is defined by the conditional probability distribution P conditioned by A is small a by this formula. This is very standard. In this way, the joint probability is written in this way. So this is the constant probability, and this is the marginal cost probability. Then the question order effect present in Clinton-Gore experiment is as follows. From the data of the opinion poll in the US, we consider the two questions. C, Clinton is honest and trustworthy. D, Gore is honest and trustworthy. We consider the two projective random variable or quantum observable A. So if A is Y, yes, if yes, for C, and A observable A has value N if the question C is no. Okay, and B takes value Y if yes for G, and B takes value N if no for G. The question order effect has been found in this data in this way. So if you change the order of the question, the probability distribution are different. This is present Garrett poll in 1997. So if you ask the Clinton first and then Gore, then joint probability for Clinton yes, Gore yes is 49%, and Clinton yes, Gore no is 4.47% in this way. If you ask Gore first and Clinton second, then Clinton yes and Gore yes is 56.25. So there's a difference of this joint probability for same answer. In this way, all these change. And if you consider the marginal probability, if you ask Clinton first, the marginal probability for Clinton yes is 53.747. But if you ask Gore first and then Clinton, then a marginal probability for answering Clinton yes is 55.8. So the marginal probability increases in this if you change the order. Now, such a order effect is considered to be a result of some quantumness in our mind. So we consider the standard quantum joint probability. Standard quantum joint probability, the joint probability of projective measurements in quantum theory, is defined for two observables or two self-adjoint operators, AB or two projection AB, and the state vector psi by this way. So you measure A first, obtain value small a, B second, obtain value small b in the initial state psi is calculated in this formula. So state psi is projected on this projection for the eigen subspace of the observable A with eigenvalue small a. Then this state is all again projected on the eigen subspace of the observable A corresponding to the eigenvalue small a. So this length, the squared length, is gives this probability. Then if A and B are commutative, they show repeatability. So if you immediately ask the same question, they always the same answer. But if A and B are commutative, they show the non-QoE, there is a commutativity order. So this is actually the same as the classical case. However, if A and B are non-commutative, they still have this repeatability. If you ask the same question, then the answer is always the same. However, they show that question order effect if you change the order, then the probability is different. And such a joint probability formula can be described as a projective update rule or quantum Bayesian rule. And this Bayesian rule is just change the initial state vector psi. It changes to the projected state vector, renormalized by the normal. So, using this state update rule, the joint probability is written in this form. So, this is the conditional probability. Conditional probability is given by this updated state. So, this is very parallel with the classical Bayesian update rule. Now we consider the how do processes determine observable. We talk about observable only here, but those observable are very closely related to process. Consider the rotation over the sphere. If you consider the rotation around the y-axis, then this rotation is most sensibly detected by this observer on this z-axis. So the rotation around the y-axis determines two valued observable sigma z. This is the spin observer for the z direction or z component with eigenvectors 0 ket and 1 ket. In the observable algebra. Observable algebra is a quantum mechanics usually defined by the group representation such a rotation group. And generally, yesterday Saigo's talk introduced the category algebra from the defined observables from the structure of the process category. Then one Bussmeyer model attempted to explain the Clinton-Gore experiment by projective measurement of non-commuting observed in this paper. However, their model is criticized for the failure of the RRE. And so they show this non-correlation, non-perfect correlation for the first answer and the third answer. They therefore pointed out by Krajnikov, Vasyeva, Zakharov, and Bussmeyer. This model is not reasonable for the Clinton-Gore experiment because usually we consider that those opinion poll data satisfies RRE. So, and then we obtain also no-go theorem. The projective measurement model does not satisfy both QOE and RRE. The complete proof is given very recently. So, we cannot explain the Clinton-Gore for data by the projective update model. So, we consider more general quantum measurement model. We consider more general class of measurement models than projective measurement known as quantum instrument. So, I introduced in the beginning of this talk. In quantum mechanics, normalized states are represented by positive operators with trace 1, and the subnormalized states are positive operators with trace less than 1 or equal. Now, let S be the space of state and S0, the space of the subnormalized state. An instrument X mathematically defined to map every real number X to an acting mapping IX or X into S0, such that totality of this map satisfies the changes state to state. And state update rule can be written by this mathematical structure that we should omit. From the above, we have this formula is just the product of this updated state times the probability of obtaining this result. Now, for the sequential measurements of observables on state law by instrument, sequence of instruments I1 to IN, the joint probability of the outcome is written in this very simple mathematical form. For two instruments, AIA IA/ID measuring two observers AD, the repeatability, QE, and ROE are characterized by those formulas. Question: are there any instruments IA/ID satisfying the above three conditions? Because above three conditions considered to satisfied by the opinion poll data, but the projected measurement model does not satisfy this condition. Are there any instrument models satisfied for all of those data? Yes. The no-go theorem for projected measurement model does not hold for instrument model. So we find very nice quantum instrument model. So approach from quantum instrument theory, as above, the attempt to explain the QOE in the Clinton-Bohr experiment by projected measurement was not successful. We succeeded in reproducing the Clinton-Bohr data with high accuracy by a pair of quantum instruments which model physically realizable measurement beyond projected measurement. So we construct the two instruments, IA and IB, satisfying the repeatability. A and B are commutative so that RRE holds. However, the instruments are invasive so that QOE holds. Means that question order effect manifests. This model reproduces the joint probability in the Clinton-Bohr poll data with a relative error less than 0.7%. This shows the real data and our theoretical reproduction. We determined the free parameter, just the 6 free parameter, and those free parameters is just the equivalently obtained from the real data. So real data uniquely determine free parameters, and then those models fitted by those parameters show that the very close number. So this lower number is original Gallup data, and this upper number are our theoretically produced date number according to our instrument model. Our model considered to be very successful to reproduce both the question order effect and response reproducibility effect, and also the numerically reproduce the original data very closely. Thank you very much.
Yeah, we've still got 5 minutes for questions now.
Yes, I was just wondering, did you work with a complex or real Hilbert space?
Complex Hilbert space.
And how do you interpret the Born rule?
Born rule is the usual one.
Yeah, but how do you interpret it in the case of complex numbers?
Oh,
in this case?
Complex number is the square root, square of the modulus.
So what I wanted to say, like, so it's very easy to make sense of this all in terms of, like, I'm talking about interpretation. Mm-hmm. What do the mathematical things you have mean? It's very easy to interpret it all in terms of real Hilbert spaces.
Why? No, because the if you consider the wave function, it's a complex variable function.
In quantum theory?
Yeah.
We're talking about psychology.
The same thing, because our model needs the non-commuting observers. In that case, you need the phase factor.
Oh, you can have non-commuting observables with classical Hilbert spaces as well. But you can take any matrix, any two matrices that don't commute. They're on a classical Hilbert space, they're in a product space. So what I'm saying is, like, so if you think about these models, and you think about what is the key difference that's sort of between quantum theory and the psychological context. And I think the key difference is that in quantum theory, you have a complex wave function, you have a complex Hilbert space.
Yeah.
Whereas in psychology, there is no explanation for the sort of effects you get when you use like in psychology, basically, you get away with real Hilbert spaces, and it's just a convenient tool.
Yeah.
You introduce a complex space, but the complex numbers do not have
I think no one knows the answer because the quantum logic is defined to be the closed subspaces. Yeah. And the complex Hilbert space and the real Hilbert space has a different structure of the quantum logic. Yeah. And which is more suitable for cognitive science is not yet determined.
Okay, but I think of it like you have, so if you make a model like this in psychology or cognitive science, you have to say, what is the state? What does it mean? And usually the meaning is that it tells you something about, let's say, the preferences or the internal position of the agent.
And you cannot, I think our result is the opposite, because our result shows that the logic is Boolean. Means that you don't need.
I agree with that.
So the projection belief update satisfies are independent only if it is logically classical. So, however, but still you have the non-Bayesian update.
But all of your results are true in a real Hilbert space. There's nowhere in this whole where you use the complex Hilbert space.
I don't know. Yeah, maybe so. Yeah.
Okay. Anybody else? Yeah.
In the mathematical approach to quantum probability and so on, you often ignore the measurement problem, right? Because you end up getting expectation values or probabilities. But of course, the measurement problem in quantum physics is that when you do an experiment, one thing happens and not another. It's not just a question of what happens for an ensemble, or it's not just expectation values, but you do an experiment and something happens, and the particle does go through or doesn't go through, or it goes to, and my question is if you bring these tools into psychology or consciousness, you could get the measurement problem there as well, right? Because when you do there's one thing about asking what happens when you do some statistics with thousands of people, what they answer.
No, I think that the physical experiment has a definite procedure, and they always obtain the classical result of the measurement, because the meter pointer is always show the classical position. So the result of the measurement always some classical variable.
Sure.
In the same way, the experiment for such opinion poll and all of these answering experiment for the psychological data, in which case always they obtain the classically formalized data, yes or no. And we never obtain the superposition of the yes and no.
What about all the don't knows?
Pardon?
What about all the don't knows?
What?
Well, no, sorry, never mind. No, neither of the above.
You're completely right. When you do a measurement, you get a result.
Yeah.
But the measurement problem is that we don't understand the mechanism. Why do you get one result or another? It just gives you probabilities.
Yeah, exactly.
I'm just saying that there is the measurement problem which is not solved, and these mathematical formulations of it don't solve the measurement problem in quantum theory.
I don't think that such a measurement problem causes any inconsistency for the theory.
No, it's not inconsistency. It's just
So what's the problem?
It's incompleteness of our understanding of physics. We just don't know.
No, it's a complete. The physical theory is a complete logical theory.
Incomplete in the sense that something happens in physics that we don't understand.
It depends on the interpretation.
I think we've gone over now,
Yeah.
unfortunately. This could be good for a discussion session if we want to go into anything to do with measurement problems and so on. But let's thank Professor Ozawa.